All right, in this example, we are going to explore the p-value method for doing the z-test for a proportion, p. Okay, we're looking at example 8-20. This is still in section 8-4, still talking about the z-test for a mean, looking at example 8-20. And we're located on page 456. Yeah, okay. Kind of like a pattern. All right, so let's go ahead and read the problem. Right, it's on the subject of attorney advertisements. An attorney claims that more than 25% of all lawyers advertise. A random sample of 200 lawyers in a certain city showed that 63 had used some form of advertising. At alpha equals 0.05, is there enough evidence to support this attorney's claim? Use the p-value method. Okay, so that's the nature of the problem at large. Those are the specifics of this particular problem at large. And in order to explore the p-value method and this concept of the z-test for p a little bit more in depth, we're just going to go through the original example, and then I'm going to do a couple of different variations where we just modify, just a small portion of it and see how that changes the results. Okay, so let's get started. Just first of all, in the original, let's maybe jot that down. Original. That's all I can do to spell it. We have for p, for the conjectured proportion, it says at least 25%. So that's our benchmark that we're going to set the proportion equal to in the null hypothesis in h subscript 0. We're going to say p equals 0.25. Random sample of 200 lawyers. So there's n is 200. Okay, showed that 63 had used some form of advertisement. So X is what we call the number of items that have that particular attribute that we're looking for. Alpha is equal to 0.05. All right, so there we are. There's alpha, and that's all we need so far. Okay. And I'll just mention the ways that we're going to switch it up to create a little bit of variation and notice those different things. So I'll just kind of give you a preview or outline those. So I'm going to go through the original problem and see what happens, see what the result is. And then we'll redo that, and we'll use a different value for alpha. Okay? And then to just, give it more variety, just explore a little bit more, we'll go back to the original standard value, 5% for alpha, and we'll start to go ahead and tweak this value, all right, and see what happens when we change the information from the sample itself and explore what that looks like. So we'll have X, in one case we'll have it be higher, in one case we'll have it be lower. All right, so that's just a little preview of different ways that I want to do this problem. Okay, so let's just go through step by step. Step 1 is identify the hypotheses and the researcher's claim. So for h subscript 0, we have p equals 0.25. For h subscript 1, we have p is greater than 0.25. Step 2. For the p-value method, step 2 is to compute the test statistic. And so in this case, we're computing the z value. So remember what we always have to do. We have to try to recreate the formula, so I'll just give you the time to do that. Okay, here it comes. P hat minus P all divided by the square root of P times Q over N. So over here I've included the scratch work really quickly. We have P hat is defined as X over N. So that's 63 over 200, and quickly calculate that as 0.315. Q, we have to calculate that as well. So that's for the population, remember, so that's 1 minus P, not P hat. So for that, 1 minus 0.25 gives us 0.75. Therefore, we put it all together as 0.315 minus 0.25, all divided by the square root of the entire thing, 0.25 times 0.75, all divided by 200. And we get out 2.12. All right, so on to step 3. We'll flip the page here. Okay, in the p-value method, step 3 is to calculate the p-value. And so we're going to find p of 2.12. Well, no, sorry. We're going to find this area, all right? So remember, when we look up p of 2.12, that's going to give us a left area. That's going to give us all of this stuff, the shaded in purple area, okay? So we're going to have to look that up and then do 1 minus that, all right? You know, I never want to do that, so remember that that particular right area would be the same as this left area. Okay, so let's just take that and plug it in, look that up, all right? It's the same area because of the symmetry of the normal distribution. And that's why I say, hey, it's the z distribution, it's the z curve. We love that one, it's great. So we have that trick of looking up the negative of the z value, the opposite p value, whenever we have a right area. Okay, so for this right area, negative 2.12, plug that in, it yields an area of 0.0170 is the value I see in the table. Okay, so that's our area. That is our p-value. So here, let me change this up a little bit. That would be technically the probability that our z-score is less than 2.12. What we are actually doing here, we're not going to even mention 2.12, we're just going to call this the p-value. We're going to say the p-value is equal to 0.0170. Okay? And so now, when we go to step 4, make the decision. Okay? Our p-value, you know what? Don't want to bother rewriting it. Our p-value is 0.0170, and that is less than 0.05, which is what alpha was equal to. So if our p-value is less than alpha, we reject H subscript 0. We reject the null hypothesis, like that. Okay? And just as a matter of explanation, here, let me try to erase this red shading here. As a matter of explanation, just comparing the p-value method and the traditional methods, okay, together, just once again. Normally in the traditional method, we would go ahead and look up our critical value. Remember this one. Don't hate me if I'm wrong, but I'm just going to go from memory. As we recall, that's 1.96. And this red shaded in area corresponds to exactly 0.05. So that's how we found that critical z-value. And we would then say, well, is 2.12 in that region? Instead, when we're just calculating the numerical value, we don't have to have this picture in mind here, all right? It helps, to think about it, to analyze it, to come up with the correct p-value. But then we don't even have to think about the z-score itself. We look at the p-value and just compare it directly to alpha. If it's smaller, we reject the null hypothesis. I believe if it's less than or equal to that, we reject the null hypothesis. So if it's right on the boundary line, we count that as the rejection region. Okay? So we reject H subscript 0, and then we're going to summarize. So that will be step 5. Oh. So we can summarize it as follows. The evidence suggests that more than 25% of attorneys use advertising. Okay, so basically in these new variations that we're going to do, step 1 will automatically be the same, exactly the same. The test value will be different because we're going to change some of the details of the problem. The p-value obviously will be different. If the z-value is different, then we have a different p-value for it. And then the decision-making process will work the same way that the p-value method always does. So let's do part B. Even though there is no part B, I'm going to say that part B is pretend it's a brand new problem. All of the details are the same, but in this case we're going to just modify alpha. We'll just say, let's test this claim, and instead of using alpha equals 0.05, we'll use alpha equals 0.01. So, just to go through briefly, step 1, exactly the same. H subscript 0 reads P equals 0.25, and the alternative hypothesis H1 is P is greater than 0.25. Right, in step 2, we have the same X, the same sample size N, so we have the same sample proportion P hat, and thus the calculation for our test value Z gives the exact same thing, 2.12. And since we have the same Z value and we have the same right area, we have the exact same P value too. Okay, the only thing that's different, potentially, well, the first place we spot a difference is here. We notice that, where did it go? Oh, there it is. 0.0170 is greater than 0.01. Technically, 0. This is our p-value, and this is alpha. So notice the p-value is strictly greater than alpha, and so in that case we don't reject H subscript 0. And so because we came to a different decision, because of essentially the different strictness of the test. So when we lower alpha, it's almost as if we have to get even stronger evidence to make us reject the null hypothesis. So it becomes a more a powerful test. It's a stronger statement if you have a lower alpha. And so that means that if we reject the null hypothesis for some level of alpha, if we decrease that, we may not reject the null hypothesis. If we increase alpha, I'm not even going to write this down, but let's suppose they asked us to test this claim at a significance level alpha equals 0.10, like 10% significance level. All right. Well, there our p-value would still be 0.0170, okay? And notice 5%, I I can't write it here. 5% is greater than 1.7%, all right? And so if we pass to any higher value of alpha, like 10% or even 7%, whatever, we will still reject the null hypothesis. So if we reject the null hypothesis at some level for alpha, any higher level of alpha, we will also reject the null hypothesis. But notice, if we lower alpha, then that may cause us to have a different decision, as we saw here. Okay, now I'm calling it C here, in this third variation, we're going to switch back to our standard level of alpha, standard significance level of 5%. But now, this time, we're going to suppose that x equals 73. So what I mean by that is the same information, but let's just suppose that instead of finding 63 attorneys who had used some form of advertising out of this sample of 200, let's suppose that we found an even larger amount. Let's say we had 73 attorneys, and we still wanted to test this same claim. All right. So, well, okay, so 1 is the exact same. We still have the null hypothesis, p equals 0.25, and h1 is p is greater than 0.25, so that's exactly the same. And step 2, we have a different sample, right, essentially, right? We're supposing that the sample was different, that there are 73 attorneys that advertise out of this sampling of 200. So that means, of course, that our test statistic is different because we're going to have a different value for p hat. That means, so we calculate our test statistic the same way that we always do. Z is equal to p hat minus p, all divided by the square root of the whole thing, p times q, all over n. So we plug in everything that we have. This time it's 0.365 minus 0.25, all divided by, look, the denominator is the exact same. And here we got 3.76. Okay, so moving on to step 3, where we compute the test value, the p-value. Just, we don't have to do this sketch, but, it helps to have a kind of mental picture of what's going on. So here we're saying here's 3.76. Said the wrong thing. Okay, and we're looking for, since that's a positive z value, we're looking for the right side area. So we're looking for this area, shading in here. Okay, so here we're going to plug in 3.76 into our z table, and then do 1 minus that since it's a right area. Or we could be sneaky, flip onto the other side, and plug in negative 3.76, and just take that value as it is, because that would be a left area, but that would be the exact mirror image, left area, as our right area. But there is a problem. You look on the positive side, it only goes up to 3.49. You look on the negative side, it only goes down to negative 3.49. So here's the thing. Some z tables go all the way as far as 3.76. Some go as far as 4.0. Ours only goes to 3.5. However, here's the rule of thumb that we're going to use. If our z-score is off the charts, so to speak, right, we're just going to say, all right, that area, if it's a small area like this, if it's the right area and that's a positive z-score, we're just going to say it's 0.0001, right? Or if we're looking at the opposite or the complement picture, if we're looking at this left area, and again, it's a z-score that's off the charts, so that left area would be the exact value, the exact visual representation of what that value means if we plugged in exactly 3.76. So if we have a value like that and it's a large value, we're just going to say it's 0.9999. We're just going to say we're 99.99% sure that it's below this certain value. All right. Okay, so what do we see here? In step 4, where we make the decision to either reject or not reject h subscript 0, we get the same result as the first time, because here our p-value is even smaller, right? And so obviously if we have an even smaller p-value, then that's still going to be lower than whatever our alpha was, all right? So that means if we already rejected the null hypothesis when we had some p-value, and we change our sample so that we get an even smaller p-value, then we still reject the null hypothesis because it's even further into the critical region, the rejection region. All right, so for step 5, since it's the same, since we've already covered both possibilities, I'm just going to say check, wave my hands out at, and move on to the next thing. Okay, and so I'm calling this one D. This is the fourth variation that I'm doing for this problem. This is our final redo. And in this one, we're going to just have it read the exact same as the original problem. We're just going to use 53 for X. So here the problem would be an attorney claims that more than 25% of all lawyers advertise. A random sample of 200 lawyers in a certain city showed that 53 had used some form of advertising. At alpha equals 0.05, is there enough evidence to support the attorney's claim? Use the p-value method. All right, so again, we're just doing another example, just like we did last time. Here, we need to kind of be aware of what we're doing. We need to analyze what we're looking at. So notice x is equal to 53. We compute p hat by doing 53 divided by 200, and we get 0.265, 26.5%. All right. So we're trying to substantiate the claim that the true proportion is greater than 25%, and we have a sample that is just barely greater than 25%. If this were lower than 25%, we would not even bother testing this claim. We would have any scenario not give us enough evidence to substantiate this claim. So we would maybe want to, try to, prove a different hypothesis, or test a different hypothesis, I should say. In this case, number 1 is the exact same. Number 2, we have a different sample, so we have a different test statistic. Here is the work shown here, 0.265 minus 0.25, all divided by the square root of the entire thing, 0.25 times 0.75 divided by 200. And so we get out, as a result, 0.489, so we round it to 0.49. Okay. For the p-value method, the third step is to compute the p-value. So we're looking for the area to the right, because it's a right-tailed test. Our z-value is on the right side of the distribution. There's 0 right in the middle. Okay, so we're looking for this orange shaded in area here. Okay. I'm just going to our z-table. We can plug in positive 0.49, and then don't forget you got to subtract that away from 1, or you got to be sneaky, and here we plug in negative 0.49 to get this, this mirror image left area there, right? That has positive 0.321, and so therefore this orange symmetric picture is the exact same thing. All right, so look at this. In step 4, we're going to go ahead and make the decision. The p-value is So the p-value is 0.3121. That is much greater than 0.05, which is what alpha was equal to. So p is greater than alpha. Don't reject the null hypothesis. And so for step 5, what happens when we don't reject the null hypothesis? We say there's not enough evidence to support the claim. Or whatever it says in H subscript 1, because that may or may not be the claim. All right, so let's conclude there for a thorough example. 25 minutes example.